My name is Ray Chang. I'm the Senior Manager of the Application Group of the Spectroscopy business at Thermo Fisher Scientific. Today, I'm joined by Dr. Jennifer Lynch, Research Biologist, Chemical Science Division at the National Institute of Standards and Technology. Jen is also the co-director for the Center for Marine Debris Research at Hawaii Pacific University. We're going to discuss the problem of plastic pollution, specifically the challenges in understanding microplastic contamination or pollution. Jen, thanks for joining me today.
Thank you very much. I'm happy to be here.
Can you just tell us a little bit about your career as a research marine biologist?
Yeah, sure. Well, I have been in this field since 1998, so been quite a long run so far. I can't believe it. So I got my PhD at Duke University studying organic pollutants, things like PCBs, pesticides, in the tissues of sea turtles that we were catching in Core Sound, North Carolina. And so I studied the concentration of those compounds and how they might impact sea turtle health for my PhD. And then that took me down the road a little bit south to Charleston, South Carolina, where I became a postdoc at NIST, National Institute of Standards and Technology. And there I was helping NIST develop standard reference materials, so certifying standard reference materials for new emerging organic pollutants like brominated flame retardants and perfluorinated compounds. And through that journey, we also have a biorepository, so a specimen bank where we archive animal tissues in liquid nitrogen freezers in the state-of-the-art clean room situation in Charleston. And that was expanding around 2010, and it expanded into the U.S. Pacific Islands, which led me out here to Hawaii several times a year to collect sea turtle tissues, and we also bank seabird eggs as well as marine mammals and some coral tissues in the biorepository at NIST to look for contaminant monitoring. And through those trips out here to Hawaii, one of the things that we were recognizing over and over again is it wasn't these invisible pollutants that seemed to be a problem here in Hawaii. Instead, it was this visible contamination of the beaches and around the animals of plastic pollution. And so that sort of shifted our focus towards that. And I moved here in 2014, here meaning Oahu, the island of Oahu in Hawaii, relocated by the National Institute of Standards and Technology. And I became stationed for NIST at Hawaii Pacific University. And last year, in January 2019, together, NIST and HPU, we formed a cooperative agreement that is set to establish a research center called the Center for Marine Debris Research. And so we focus on all sorts of questions about plastic pollution in the oceans.
All right, that's quite an interesting journey. You mentioned a lot of things in your career, right? I mean, you talk about POPs, you talk about the PCBs, organohalogen contaminants, all these things. If you look at the recent history about environmental study, in 1960s, people doing radioactivity studies, the heavy metal study. Then from 70s, 80s, people start to move into, other contaminants or pollutants. And more recently, we talk about microplastic or nanoplastic, the plastic pollution. That's, why we're here today. Maybe, give us, give us a magnitude of the issue we are dealing with. So help people to understand, what is the severity of the issue we're dealing with here.
Right. That's a really great question. And to put everything into perspective, I start with, because I come to you as a toxicologist, I start with the dose makes the poison, right? And so when we're dealing with invisible chemical exposures, we've really focused a lot of our efforts on things that are incredibly toxic, dioxins, PCBs, certain organochlorine pesticides, these things that we know at very, very low doses can cause significant health issues for animals. When we think about plastics, we don't think about them as being incredibly toxic, right? We actually put our drinking water inside a plastic bottle, so that plastic bottle can't be that toxic because, the human population seems to be doing just fine after drinking out of polyethylene terephthalate bottles for decades now. And so we don't think of plastics as being incredibly toxic, right? But if they're mismanaged and the waste is put into the ocean, it actually causes significant harm. And, in my research, what I have studied the most are sea turtles. And I have a long-term biomonitoring program where we are opening the guts of deceased sea turtles and looking to see how much plastic is being ingested. And it's usually incredibly shocking for people to see what we're seeing. I've become a bit desensitized to it. It is not uncommon for us to open a sea turtle that has a digestive tract about the size of mine and find 200 pieces of plastic this size. That's very common for me. So the odd thing that is that we're not seeing a lot of damage happening to the gastrointestinal tract. Turtles are able to pass things this size, and they excrete them through defecation, so through their poo. And we aren't seeing a ton of toxic effect within the sea turtles from eating a lot of that plastic. Certain researchers around the world are showing that it's definitely killing turtles. So there can be lethal impacts through gut obstruction, perforation, and gut torsions, actually. I think one of the biggest damaging effects is if a turtle swallows a long, very line of a long fishing line, monofilament fishing line. It will travel through the gut. If it doesn't get all bundled up together and pass through the gut as one bundle, it can spread out. And as it moves through the digestive tract, it can twist the digestive tract, which can cause lethal torsions because then nothing can pass through. But more damaging than actual ingestion of plastics is the entanglement of plastics. So I know we're talking today about micro and nanoplastics, but I think it's incredibly important for us to also focus on megaplastics because that's the killer. We have certain information that megaplastics, things like giant fishing nets, which are polypropylene and polyethylene or nylon, are strangling, drowning, or causing turtles to get so entangled that they can't forage and then they starve to death. And so the magnitude of the problem is very large. All you have to do is take a little walk on our windward beaches here, Kailua or Waimanalo, or up at Kahuku, which is the worst beach here on this island. And, you'll be shocked by what you see. If you walk along James Campbell National Wildlife Refuge, which is about 45 minutes north of my home, which I'm coming to you from my home because of coronavirus right now. If you go to Kahuku, you'll be just jaw-dropped. It's a national wildlife refuge. No one lives there. It's a place where amazing wildlife are being rehabilitated, like albatross are being rehabbed there. And you walk along the beach and it looks like a trash dump because it's all washing in from far offshore. And there's just this line at the high tide line, or maybe 3 lines of trash. And there'll be items, bigger than you can pick up with one person. And then if you sit down in the sand and you start picking at the sand, you'll see microplastics galore. So we have a long-term monitoring study up there for microplastics as well in the beach sand through an undergraduate student that's at the center. So the magnitude it's really in our face here in Hawaii as we walk the beach. It's sort of jaw-dropping and stunning to see the magnitude of what's happening here on these beautiful, should be pristine beaches of Hawaii. So it's definitely something we need to take care of. We don't want our beaches to look like a trash dump because a very large part of Hawaii's economy is tourism, and we don't have any tourism now, so we're really feeling the effects of what happens to our economy when tourism drops. And we don't want that to happen once we're opened up again because of this perception that the beaches are trashed and dirty, and so something needs to be done.
Yeah, absolutely. I think, you kind of brought up a very interesting point, right? I think the fact that there is a pollution, plastic pollutants everywhere, I mean, that's indisputable. That's why they term this Great Pacific Garbage Patch. Certainly there's a lot of attention from the scientific community, from the society in general, but the question is, like you pointed out, mainly don't believe plastic are toxic. And you look at the past publication, probably dating back 2008, 2009, this is a period we see exponential growth of publications. And yet, majority of those publications are focusing on detection, identifying, the polymer species. And the actual study on the biological harm or biological impact are fairly scarce, right? I mean, there are anecdotal publications on that subject. So that begs the question, what needs to be done differently? We are still doing a lot of research. What are the challenges associated with, microplastic or nanoplastic? But to your point, a megaplastic, what needs to be done? What are the challenges we are facing?
Funding. It's the number one challenge. It blows my mind that we have such an environmental disaster, or maybe disaster is a little bit too harsh of a word, a calamity, right? This is ugly and it shouldn't be happening to our oceans. Yet we have such little funding to do anything about it. And, we have started this research center as sort of a grassroots effort. The far majority of our funding is in-kind donations of instruments and of people's time and effort. The far majority of the people working at the center are unpaid students that are volunteering because it's passion projects. And the far majority of our beach cleanup efforts, passion projects, it's all volunteer, it's all nonprofit efforts. There is no, I shouldn't say there's no state-directed funds at this. There are some state-directed funds at like removing derelict vessels that have sunken to the bottom. And of course they have plastic in them too. But there's very limited funding available, especially in the United States. Now, Europe is different. Europe has had a lot of effort, a lot of funding directed towards them. And in a 2018 publication, I sort of brought that to light for the sea turtles because there's this tremendous effort and resources and funding directed towards plastic ingestion in the European waters. Yet, if you compare the sea turtle ingestion amounts across the globe, the effort is very disproportionately provided because in the Mediterranean Sea, the sea turtles there are not eating very much compared to what is here in the Central Pacific, which is just extraordinarily more. And so it's surprising to me that society hasn't gotten behind a lot of this to help fund it. through either federal, state, or nonprofit donation style. And it seems to be more of a grassroots effort, but that's the number one challenge. There are additional challenges, so I'll talk about those a little bit too. I'd love to go to just jump to the nanoplastics, right? So nanoplastics are still something that are out of our reach. There is not yet a research organization, certainly in the US, maybe there's 2 or 3 in Europe that are attempting and getting very far with trying to detect nanoparticles from environmental samples. And so NIST has done a little bit of work with JRC in collaboration, but they've only focused on a single polymer, and their methods would not allow them to differentiate different polymers from an actual sample. So everything has the instrumentation that is available to attempt to measure nanoplastics in the environment needs a whole lot more effort and more development. I think there's some promising techniques that are out there. But just to give you an idea, you must have a scanning electron microscope, right? Because we're talking about particles that are smaller than 1 micrometer. So you have to have these very powerful microscopes. I don't have something like that available to me here in Hawaii. NIST has these things in the DC area. So nanoplastics are completely out of my reach. It's not something that my research center will be focused on doing because we would need millions of dollars to set something up like that. So those kinds of research projects need to happen in large research core institutions back on the mainland, right? And so once you can see the nanoparticle under a scanning electron microscope, that's not going to tell you whether it's sand, a skin particle, if it's hair, or if it's a plastic. You have to have some kind of chemical detection capability connected to that microscope to be able to identify what is the chemical composition of that particle. And that's where I find the challenge really lies. Raman microscopes today, they can get down to 1 micrometer, but not into the nano range. And the nanoparticles are something of concern in my mind because scientists do believe that they can cross the gut-blood barrier and then be mobilized into other tissues. If they can do that and they can make it to the brain or the liver or other organs where you don't want unnatural particles in those places because bad things could happen, right? So it's still a hypothesis, it's still a theory, and it's remained unproven at this point.
Yeah, no, that's really interesting. You talk about nanoparticles. Many believe, or at least we start to agree on the fact, a microplastic is transitory state between macroplastic and a nanoplastic, right? But is that fair to say even for microplastic, we are still facing a lot of challenges from a research standpoint, right? Maybe we can just dive into that a little bit. I know you've been using FTIR microscope, you worked with, I know the scientific community is using Raman microscope, but there are other techniques out there. Maybe, you can share with us your view on that. Even at the micro scale, talking about, particles that's greater than 1 micron, what kind of a challenge you are facing today?
Yeah. I'm happy that is my world for sure. That is the world that I am struggling through right now. So I have used both a Raman microscope and the FTIR microscope on the same samples and complementary. The two methods are incredibly complementary because FTIR can detect certain polymers and the ones that it's not good at seeing, so Raman is good at seeing. So if you can get both on each individual particle, you've got a lot more confirmation of the polymer, as well as additional information to say that, yes, certainly that is plastic, or if it's not plastic, it's most likely man-made or man-synthesized or man-used, right? And I can go into details of that in a little bit. So, but your question led my brain to, as I'm setting up a lab, right? So our research center is fairly new, and we're dreaming about what instruments we would purchase if we had center, millions of dollars of funding. And when I dream about what that lab would look like, my vision is to have, I call it the Trinity. The Trinity of instruments for microplastic would be a microscope FTIR, a microscope Raman, and a GC, pyrolysis GCMS, because that's sort of the Holy Trinity in my mind. Because when we think about what units people want to know for microplastics, there is a whole camp of people that want to know how many particles, what size distribution are those particles, and what is the polymer composition of that population of particles, right? And the only way you can get that is a microscope FTIR or a microscope Raman, because that can do the individual particle count, sizing, and polymer composition all in the same mapping automated run. Then there's a whole other camp of people that want to know, like toxicologists, they want the units to be on a microgram polyethylene per gram of tissue, or per gram of sediment, or per gram of sludge, right? And so they want the concentration units in a mass fraction. And you can estimate based on the size of the particle that you measure under the microscope, Raman or FTIR, and the known density range for each polymer, you can sort of estimate the mass of each particle, but you're making a lot of assumptions. You don't know the depth of the particle. You don't know its true density, because each polymer has a range of densities. So you're making a lot of assumptions and tabulating that up and summing all that variability and uncertainty when you do that. But pyrolysis GCMS can give you an accurate known concentration. But what it can't do is tell you how many particles and what sizes they were, because basically you're burning the entire sample and you're losing that information when you do that. So to me, the Trinity would be all three, and you analyze every sample on all three. Now the time limits on that would be giant, but NIST usually encourages me to go more towards the time-intensive and accurate and more information-intensive route than a more screening route that other labs might want, where they just want to have some sort of idea, and it doesn't need to be incredibly accurate or precise.
Okay. You mentioned three techniques, right? Vibrational microspectrometry could be both FTI and a Raman, and you mentioned pyrolysis GCMS, and I think upon reading up on that subject, right? There are multiple issues we have to deal with. Even for the vibrational spectroscopy, one of the issues is the library identification, for example, right? I mean, we are coming from a world where my reference material or those entries in the library are virgin standards, whereas in your case, the sample was never a virgin material. It's being weathered. It's under different subject to different chemical, maybe under UV light, all those degradation process. And, to that end, can you comment, how do we go, about doing that?
Yeah, so all three of those techniques in the trinity that I mentioned have method development that still needs to be done. We're nowhere near cookie cutter science with standard methodology. We're still trying things out. And as you said, the spectral library limitations are one of those. That's just one step that needs to be better looked at and better understood. And so what we do in our lab is we make our own in-house library. We have about 100 different plastic polymers that we've sourced from various sources, and they actually range from everything from like a scientific standard, like a NIST standard reference material of polyethylene, all the way to a shampoo bottle that we brought in from our house because it's a consumer good and we know that it's got many, many additives, many colorants. All of that is already in it, which is more representative of what we see on the beach and out in nature than, say, the NIST standard reference material, right? And so we kind of grade all of our reference polymers across a spectrum of scientific standards is the most pure grade, but even then, people need to know that those scientific standards are usually procured from a pellet producer that additives have been added in there. And the additive package is usually proprietary, so no one will know exactly what that is except for the manufacturer, and that's not divulged when given the standards. So you always have this, you have to assume your plastics you're dealing with, whether they're purchased brand new from a scientific source or they're a consumer good, you have to assume that there's an additive package in there. They're not going to be just 100% pure polyethylene, right? So we have scientific standards. Then we purchase some standards from companies that are pellet producers and just distributors of plastic. We also receive plastic from some industry partners that are willing to share with us to help us bring our laboratory up to speed. And then we have the consumer goods. And we like to have all three kinds of references for each polymer so that we can see how different they come across on an FTIR. And FTIRs are quite, searching for the right word, they don't detect the additives very well. And we use that to its advantage because we're more interested in identifying the polymer than we are the additives that are in there. And so by the FTIR being more blind to the additives, it's helping us out. And so we actually like that. But then we have a whole research project that's involved in understanding what the chemical additives are and how they're leaching out of the plastics and into tissues. And that those scientists need to know what the additives are. So going back to the spectral library searching issue, we've recently done a very quick test where we took a few of our samples and we ran them through 3 different libraries, actually 3 different sets of software that had different library packages in them. And the answers that you get back, your top hits across all 3 different software packages with different libraries involved are very different. And I shouldn't say very different. We get different chemical answers, but they're sort of all in the same chemical family, okay? And so, for instance, a lot of these are, we find a lot of fishing lures. So those wiggly little fishing lures that, fishermen use to attract fish, those are made with a very high percentage phthalates. And the phthalates actually do show up on the FTIR. So we are able to look at phthalate additives and as long as they're a high enough percentage using the FTIR. But we want to know which phthalate is the bulk material that's inside this wiggly little fish lure. And when we run it through one set of software, we get a very different hit than when we run it in different software with different libraries. And the reason is solely because each library has a different set of phthalates that are included in that library. And so the top hit is going to be the one that matches the best, but it might not be the one because that library might be missing that phthalate additive, right? And so that is a challenge for any spectroscopist, right? Because your library is, your top hit is only as good as your library is. And there are thousands of different phthalate chemicals. And for one lab to source all of those and have an in-house library of thousands of phthalates is, well, cost prohibitive because I can't purchase those at that number. So that's definitely a limitation. Another limitation is that the FTIR spectrum changes with weathering. And I wouldn't say that that happens so much that you can't identify the polymer, but it does make your spectrum more noisy. And then your top hit in a library search might be inaccurate. And it does take some manual visual looking at the spectrum to really decide and to use just common sense. That I've seen some publications that put out only their top hit, and that's just what they used for their polymer ID. And their top hit was something that would be a liquid phase at room temperature. So it could not have been a polymer in the ocean. And so there's some, just chemical knowledge. The human brain needs to be double checking these top hits. You can't just go with that. You've got to use some common sense there. And one of the things that we certainly see in our FTIR spectra that we wish so badly we could differentiate is low density polyethylene from high density polyethylene, because these are totally different plastics. They're produced for different reasons. They have totally different resin codes, the chasing arrows sign on the bottom. And we want to be able to differentiate those, because certain ones, the high density polyethylene, the number 2s, are recycled a whole lot more frequently than number 4s, the low density polyethylene. So we have different uses for these things, and then we have different waste streams for these two different polymers that are so similar. And if we want to track changes in the environment based on society changes of changing recycling patterns or changing policies against certain polymers, right? We have to be able to differentiate these two. And what we've noticed in our recent research, back in 2018, we published a paper, Young et al., it's called Validation of the FTIR for Marine Plastic Pollution, something like that. And it did say that we could identify low density from high density 85% of the time. We kind of want to walk back that a little bit, because that's not really true when you get into weathered polyethylene. When you get into weathered polyethylene, the high density polyethylene, which is lacking a particular band in the spectrum, that band starts to grow as weathering happens. And so it starts to mimic the low density polyethylene spectrum. And so when you're dealing with weathered polyethylene out there in the marine environment, which is what we're dealing with, you actually shouldn't use the FTIR to differentiate those two. So that's been a tough learning lesson, because we very much want to be able to do that. So we've had to go to a different instrument for doing that.
All right. Fair enough. I think I have a couple of comments about, HDP versus LDP, right? But there are certainly publications using both mid-IR and the near-infrared to differentiate. The combination of spectra with chemometric method for example, discriminant analysis. The other interesting thing you pointed out, when, a high density, the chemical difference between HDP and LDP is the crosslinking, the level of crosslinking, the branching. When you put those material under a weathering condition, it could very well be some of the, networking is broken down. So it's more mimicking LDP, from a 3D networking, condition. So yeah, I just can't see, I agree with you 100%. A lot of challenges. Put aside the HDP, LDP, just in general, when you have a non-standard material or chemically degraded material, search against, commercial library, that's going to be a big challenge, how to reconcile the data. To that, are you aware of any community effort, if you will, or concerted effort, by different research organization, research group, trying to pull the data together such that, we can move a little bit faster?
Yes, thank you for bringing that up. Yes. So Chelsea Rockman's lab has created her own in-house libraries called SLOP and SLOPy. I like her little acronyms, they're fun, of non-weathered and then weathered plastics. And she's showing that she gets much better, more accurate hits when she's using her own libraries than, say, just commercially available ones. And so I know of that work, and then I also know of Speccy. And this is a free online open source spectral library search tool that Wynn Cowger from University of California, Riverside has developed specifically for the microplastics research community. Myself, Chelsea Rockman, Sebastian Prümke's lab in Germany, and several other labs have uploaded our reference libraries into Speccy, and so it's already available and online for the community to use. And I believe Wynn let us all know that there were approaching or over 100 different active users of it right now. So I know that it's getting to, it was either 45 or 100. I wish I could remember that number. I'd have to come back and tell you what that number was. But really good community use of this free online tool. And so we're really excited to be a part of it. Chelsea and I have tried to break it. So we're trying to throw very challenging pieces at it to see what it comes up with. And I've been able to break it, so it's not perfect. But it will improve as more and more spectra are added into that library and more people begin to test it and break it themselves to figure out how we can improve it more. So I think it's a very important tool that a lot of people are really excited to have out there.
Yeah, no, absolutely. I know there's a lot of research effort, but from our standpoint, right? I mean, Thermo Fisher being one of the largest scientific instrument vendor. I mean, this effort, why we are really keen on being part of it, in whatever is possible, is being the citizen of the planet. And also, if you look at Thermo Fisher, the company is really to enable customers like yourself, right, to make the world healthier, cleaner, safer. So yeah, we all have a great deal of interest in being part of this, great effort and contributing, to this great effort.